Alrighty, we're going to get started. Welcome everybody to the first briefing on Wednesday morning at 10:15 a.m. Pacific time, titled Stars, Their Environments, and Their Planets. I'm Haley Wahl. I'm the AAS Media Fellow, and I'm assisted today by Susanna Kohler, who is the AAS Deputy Press Officer, who will be helping with tech issues if they arise. And over here at this little table, we also have Carrie Hensley, who is the Deputy Press Officer for AAS, who will be helping with the Q&A online. And we also have Briley Lewis, who is the AAS media intern, who will be assisting with the in-person questions. So there are at least 6 press releases going out today for our speakers. And the videos and the slides and everything from Monday and Tuesday are already up online. The press releases are also on the Slack. And so you can just go to the meeting website and find those. Quick overview of how this is going to go. So we are recording the briefing and streaming it live to YouTube right now. I will give a brief introduction to the topic and the panelists and their presentation titles. All of the panelists will speak in order. We're going to start with the virtual panelists and have them go, and then we are going to continue from the right all the way to the left. We are, for the attendees on Zoom, please type your questions into the Q&A, and I'll remind you about this at the end, with your affiliation and who your question is for, and same with the in-person attendees. When you ask questions, please state your affiliation and who your question is for. So again, this is the Stars, Their Environments, and Their Planets session. Our speakers are, first up online, we're going to have Michael Jones from the University of Arizona with a talk titled Young, Blue, and Isolated Stellar Systems in the Virgo Cluster. Next, we'll have Evan Rich from the University of Michigan, who is also virtual, with a talk titled A Survey of Pre-Main Sequence Stars and Massive Tauri Planetary Disks with the Gemini Planet Imager. Next, we'll have Tony Wong from the University of Illinois, Urbana, Champaign, with a talk titled ALMA Unravels, a Star Formation Standoff in the Tarantula's Gaseous Web. And then next we'll have Adina Feinstein with a talk titled Far-Ultraviolet Flares on AU-MIC and Implications for Its Planets. And then finally, last but not least, we'll have Rafael Luque with a talk from the University of Chicago. And Adina is also from the University of Chicago with a talk titled The HD 260655 System, 2 rocky worlds transiting a bright M dwarf at just 32 light years. So I will hand it over to the virtual presenters.
And give us just a second so we can make sure that we are all able to see your screens. Let's see.
Should I start sharing now?
Give me just a moment. Yeah, go ahead. Let's see. Okay, I think we are good.
Okay, I'll get started then. So hi, I'm Mike Jones. I'm a postdoc working at Steward Observatory. And today I'm going to talk to you about these blue isolated stellar systems in the Virgo cluster. And we think these are a completely new type of stellar system. So I'm going to be explaining about those and why we think that. So we've detected all of these 5 systems in the Virgo cluster. So I want to just start by giving an overview of that environment and what that's like. So the Virgo cluster is the nearest galaxy cluster to the Milky Way at a distance of about 50 million light years. And like all galaxy clusters, it's filled with hot ionized gas that we call the intracluster medium or the ICM. And this hot gas is a very hostile environment for the cold gas that galaxies need to form new stars. And when a galaxy, even a pretty large galaxy similar to our Milky Way, when that falls into a galaxy cluster, it will rapidly lose its cold gas because of this hostile environment, and then it can no longer form stars. And so this is why most galaxies and galaxy clusters are what we call red and dead. And they're red because they only contain old red stars, and they're dead because they have no cold gas with which to form new stars. So it was very surprising to us when we identified these tiny isolated stellar systems that are full of blue young stars floating in the middle of this really hot, hostile medium. And when I say stellar system here, that can mean many things, but in this case, I'm meaning it's a collection of stars that's more than just a cluster of stars, but not quite enough to constitute a galaxy. But I'm actually going to start referring to these objects by their colloquial name that we use, which is just blue blobs. And the reason we call them blue blobs, if you look over in this Hubble Space Telescope image, you can see that the structure of these objects looks very blue and blobby. And these are just the brightest, youngest stars that you're seeing in this image. Overall, these objects are about 1 million times less massive than our Milky Way. So they're really quite tiny. Each contains on the order of 10,000 to 100,000 stars. And as I said, we're just seeing the brightest stars in this image. So when we found these, it was immediately a question of how did they get there, and how can an object that's so tiny survive in this really hostile environment? So to begin addressing that question, a good place to start is to ask where they came from and what they're made of. And by this, I mean, what's their chemical composition? So for a normal galaxy, what happens, a galaxy will form generations after generations of stars successively, and each generation creates, as they die, heavy elements that go into the gas of the galaxy, and they increase the number of heavy elements in that galaxy's gas. And that's what we call the metallicity of a galaxy. So for normal galaxies, which are shown with these gray and white points here, as the galaxy gets larger and brighter, its metallicity increases. It has more heavy elements in its gas. And so that's what the trend for a normal galaxy looks like. But our systems are way up here. They don't follow this trend at all. They're about an order of magnitude more rich in heavy elements than a galaxy would be for the same luminosity. And this is really a telltale sign that these objects formed from gas that was pre-enriched, and that's gas that's stripped from a large galaxy. So how do you do that? There's two main ways to strip gas from a galaxy. The first is known as tidal stripping, and this is what happens when two galaxies, they pass nearby each other like this, or even merge. And as that happens, their gravity pulls on their outskirts and creates these long tails that stretch out away from the galaxies. The other way is known as ram pressure stripping. So as I said at the beginning of the talk, a galaxy cluster is filled with this hot ionized gas. And when a galaxy falls into the cluster at high speed, that's a lot like you belly flopping into a swimming pool. And that pressure hitting into the galaxy forces its gas out behind it, and it leaves this big trail of destruction in its wake, which is what we're seeing here. And in either of these scenarios, you can get a dense clump of gas in these tails emanating from the galaxies, and that dense clump of gas can collapse and begin forming stars. And that will make an object that's very much like our blue blobs. However, in both of these cases, you typically would find an object that's right next to its parent galaxy, really, really close in the vicinity of its parent galaxy. But our objects are really isolated. They're a long way from the nearest galaxy that they could form from. So how can that happen? Both of these mechanisms seem like a viable means to form this type of object, but how can we get them to be isolated? So this is where a key difference between tidal stripping and ram pressure stripping comes in. So generally for tidal stripping, objects that are formed by that mechanism are ejected from their parent system at relatively low velocity. And this means that it would take them a very long time to become isolated. And so they would need to be old in order to be isolated, whereas our blue blobs are full of young blue stars, so they're young objects. However, with ram pressure stripping, this can occur at very high velocity, and that means that the blue blob can become isolated while it's still very young. And to show you an example from a simulation, this is a simulation of a galaxy being ram pressure stripped at high velocity, and it forms behind it this plume of gas that's about 1 million light years long. And right at the tip of the tail, it's forming new stars. in dense clumps in this gas. And that's pretty much the mechanism that we think is occurring to form these blue blobs. And this is the most easy way to explain their isolation. So just to give you a quick summary of these objects. So we think we've found this new class of stellar system that we call blue blobs. They reside in a galaxy cluster, but they're very isolated, and they're made up of young blue stars. And together, these three things make them unlike any other known stellar system. They're also rich in heavy elements. They have high metallicity, which indicates that they must have formed from stripped gas, because there's really no way that such a tiny object could build up that metallicity on its own. And the most likely mechanism by which they could be created is ram pressure stripping. And this is because it most naturally explains all of their properties, in particular, their isolation. Okay, so that's all from me. I'd like to thank the AAS for the opportunity to present, and I look forward to any questions in the Q&A. Thank you.
Okay, can everybody hear me and see me? Great, awesome. Well, thank you very much for this opportunity to talk to you today and present results from the Gemini Light Survey. I'm Evan Rich, a postdoctoral researcher at the University of Michigan. This work has been done by a great collaboration that has worked together to put this data, but I want to highlight Jean Monnier, who's the principal investigator, who's also at the University of Michigan. So a fundamental question we want to answer, it's really key to astronomy, is how do planets form? We know planets form because we live on one, and we have an idea where they form in planet-forming disks. But there's a lot of questions that we still have, including what affects their formation, whether it's the environment or the mass of the star. If we make a star more massive, how will that affect planet formation? So first, let's think about where they form. So if you were to look at our own solar system, where you have imagine you have the sun on the left here, and Pluto would be about here on the far right. So we're looking edge onto the system. And then you just age it so it's really young. You'll have a young star that's still accreting material and growing. And then where the planets are is full of thick dust and gas that is combining together to form planets. In an ideal world, all we would do is take images of those forming planets and see how are they related to the environment and how they're connected to the dust and gas. However, with limitations of technology, there's only a handful that are known to date. And so we really need a different strategy to investigate planet formation. And today we're going to be specifically looking at the small dust grains in the disk itself. So I want to first, what do we think we should observe? So now imagine, instead of looking at the solar system edge on, let's look at it top down, where the sun would be in the middle and it's surrounded by this thick disk of gas and dust all the way around it. And we're going to put a planet right about where my cursor is and see what is the planet affect the dust like. And this is a simulation done by Jaehan Bae, who's part of the collaboration. So I'm going to let this play in time, and you'll see that as the planet forms and grows, it's going to create a gap where it's rotating around the star. And it's also on top of creating a gap, it also creates these rings. And this is predicted to be a key signature of a planet formation, that when we see this gap ring structure, within those gaps is the potential for a planet. And so this is the kind of small dust grain structure we will be looking for. So the final hurdle that we need to overcome is that stars are bright and dust is not. The stars will be around 1 million times brighter than the dust is. And so if we were to take a telescope and take an image of one of our stars, this was what it would look like, and it would be very unhelpful. However, the star light itself is actually unpolarized, and the dust light will be polarized. So if we put polarized sunglasses on top of our telescope, we can remove the unpolarized light from the star and leave the polarized light from the dust grain. So there's no more starlight in this image, and then all that's left are these small dust grains orbiting the star. And again, you see this structure where you have a ring and a gap, and it's the potential for a planet within this gap. Of course, we want to do more than just a cartoon diagram. So the observations are with the Gemini South Telescope in Chile. And then our fancy polarized sunglasses are the Gemini Planet Imager instrument. So this leads us to our survey. It's the Gemini Light Survey. It's a unique survey because we're looking at more stars that are more massive than our sun. Previous surveys have done great work looking into stars similar to our sun, but we want to ask the question, how does the environment change and the planet formation change as we were to increase the stellar mass? There are 44 targets that were imaged in total, but here's a sample of six that we were able to look at. You see a variety of shapes. So everything in the orangish red is dust. And anything that, so we see a variety of shapes and no one shape really repeats itself. Sometimes we have these ring structures with spiral arms. Other times this looks a lot like the simulation. So the top middle one is very similar to the simulation where you have this ring gap and inside could potential of a planet. But finally, we find for some of our most massive stellar objects, they're surrounded by dust and gas that don't have these features. They're relatively continuous and don't have the ring features where the fingerprint of planet formation. And in fact, we find no ring systems that are above 3 times the mass of the sun. And since these are a signature of planet formation, it indicates that something might be going different with planet formation for these more massive stars. Like all good science, it ends up that we actually ended up with more questions than we have answers. There's a sleuth of answers that could answer this conundrum, such as, for example, binaries affecting the disk. More massive stars tend to be formed in binaries. So the example for this top one on the right, there's a binary star here, and that could be disrupting the disk to the fact that the rings don't form. Another option is higher temperatures, where it's believed that the particle sticking together likes to form these ring structures. So if since these more massive stars are also hotter, that could be affecting its ability to create rings. So I really appreciate the opportunity to present some of the results from the Gemini Light Survey. This is only a sample of some of the great stuff we've been able to do. It was really interesting finding a transition between the lower mass stars or stars less than 3 times solar mass, which appear to form rings, versus objects that are greater than 3 solar masses that don't appear to form rings. And I look forward to your questions at the Q&A session. Thank you.
Okay, how's my volume? Everyone able to hear okay? Good. Okay, so I'm Tony Wong. I'm a professor at the University of Illinois, and I'm here to tell you about our study of star formation in the Tarantula Nebula. If you're interested, my science talk will be at 2:30 today in Ballroom E. So to begin with, I'd like to start by posing 2 fundamental questions which motivate our work. How does the competition between gravity and stellar feedback regulate star formation? And can molecular gas clouds still collapse to form stars in the presence of strong feedback? So the basic idea here is that in order to form stars, you need gravity to pull matter together, but there are usually other forces that are opposing that gravitational collapse. And so we give the name stellar feedback to basically the winds and strong radiation that come off of young stars. So in a sense, star formation is its own worst enemy, we like to say, because when those young stars form, they blow away the material and basically prevent further star formation, at least in theory. But specifically, we'd like to know, can molecular gas clouds still collapse to form stars in areas where strong feedback is present. So in order to answer this question, we basically targeted the largest stellar nursery in our local group of galaxies, which is called 30 Doradus. Okay, 30 Doradus is also known as the Tarantula Nebula. It's located in the Large Magellanic Cloud, which you can see here is a map of the LMC, as it's called, and it's the nearest star-forming galaxy to our own. So 30 Doradus is a unique laboratory for understanding feedback because the degree of feedback in this region is unlike anything that we can observe in the Milky Way. It's just much more active, it's much more vigorous. So despite the importance of this region, though, until recently, our knowledge of the gas that fuels star formation was limited to this red box. Okay, this is an image that the ALMA Observatory obtained early in its development. This region is only about an arc-minute in size, and you can see that it's close to this young cluster, but we're still lacking the big picture context. The nebula goes out much further than this small box. And so what we did starting in 2019 was initiate a program to map a much larger region of the nebula that you can see here denoted by this yellow line. And the resulting map of carbon monoxide emission is shown here in orange. It's overlaid on a Hubble Space Telescope optical image. And you can see that there are some resemblances between the structures that you see in the ALMA radio image and the Hubble optical image, but there are differences as well. And we're still trying to understand the forces that shape this fascinating structure. So one way that we can try to study this structure is using what's called a dendrogram. So we know that molecular clouds are highly structured in the sense that you've got these denser regions that are sometimes called cores, and they're surrounded by lower density regions called envelopes. And one thing we can do is basically produce a tree diagram that every vertical line in this diagram represents a patch of the cloud, but we connect those lines in a way that we can basically reveal which patches or clumps lie inside of larger ones. Okay, so this is what we call a dendrogram. So we've been doing this analysis on our data. This figure just shows you a subset of the dendrogram clumps to give you an idea of how the process works. It's actually completely automated within software. And you can see that the resulting clumps, which are colored on this left panel, the colors on the right actually match the colors on the left. They come in all different sizes and shapes. And so they reveal something about the complicated structure of these clouds. So when we did this analysis, we were able to measure the properties inside each clump. An important question is how much random motion is inside each clump, because that random motion we think is produced by feedback. But interestingly, we were surprised by our results. We were expecting to see a consistent picture where more random motion means more feedback dominated. So the left panel has the red regions here showing the largest random motions, but those regions don't show the most feedback domination. Okay, so we were expecting these maps to look alike. They turned out to be very different. Okay. So the clumps in the center of the cloud, although they're experiencing very high random motions, they're actually just as strongly held together by gravity as the clumps in the outer parts of the cloud. So what does this mean? Well, we're basically seeing a surprising balance between gravity and feedback, even in these central parts of the cloud. Indeed, the places where gravity is losing the battle to feedback tend to be located not necessarily in the center, but in these regions that are away from the filaments. And so what are the filaments? Well, if you look at the structure, there do seem to be these filamentary things, and we have a structure finding algorithm that draws them out as black outlines here. And if we look at those clumps which are away from the filaments, they are found to be less dominated by gravity than the ones that are on the filaments. Okay, so the ones where The filaments, the clumps that are off the filaments are the ones where gravity has less of an effect. Okay, so to summarize, we found that even in the regions that are most exposed to the feedback of these young stars, gravity can still go toe-to-toe with feedback, but feedback clearly has the upper hand in the densest parts of the cloud. I'm sorry, in the thinner parts of the cloud away from the main filaments. And we expect that feedback will continue to chip away at the cloud. That's probably creating the fragments that are off the filaments. But for now, star formation can continue in those places where gravity still has the upper hand. Okay, so these results are recently published, and please feel free to contact me if you have questions.
Yeah, no, okay. Can everybody hear me? Okay. Great. Good morning. My name is Adina Feinstein. I'm a fifth-year graduate student at the University of Chicago, and I'm really excited to be here to talk to you about some observations that are currently under review at the AAS journals, looking at flares from our 22 million-year-old neighbor, AU-MIC. So to motivate this study, I want to talk a little bit about planets and the planets that we know and why young systems, particularly the planets around AU-MIC, are really important for our understanding of planet formation. So what I'm showing here is a period radius diagram with the contours showing the distribution of transiting exoplanets that were just taken from the exoplanet archive. So here there are 3,800 transiting exoplanets, and you can see two really distinct populations, right? You see the white region that is very heavily, that is really dense in planets between like Earth and Neptune sized, and then you also see the smaller population of hot Jupiters up in the upper left corner. But what I'm not telling you here is, and what's not being shown, is that all of these planets tend to be older, on the order of 1 billion years, if not older than that. So when we first started discovering young transiting exoplanets, we were really surprised in where they fell in this diagram. So I'm plotting them here. The ones that we know of, there are only about a dozen, and they are between like Neptune and Jupiter sized, which is totally unexpected, right? Because we would have expected them to fall where all of the other older planets are. And so one of the main questions for understanding these young planets is, how do we go from a population that's located up here in the Neptune-Jupiter-sized region down into this more heavily older planet population that we know of today from Kepler and TESS? So what's really important for driving this question is understanding photoevaporation. So in the same way that when it's really hot outside, you get water that boils off, the same thing happens to the atmospheres of these exoplanets. And when you're located around a really young star, the environments are a lot harsher. So what I'm showing here on the x-axis is just age of the system, and on the y-axis is the X-ray luminosity from different types of stars, going from G-type stars like the sun in yellow all the way down to our low-mass stars like M stars in red. And so if we really want to understand how the older population of planets is formed, we really need to highlight this. Ooh, sorry, that's really sensitive. We really need to look at this really young region where the stars are very active for a long period of time, and then try to observe actual atmospheric mass loss. And so young stars, they don't behave really well like this. They're not just stable over time in their X-ray luminosity. Just like children, you know, they have tantrums on short timescales. But for stars, it's less about throwing blocks or drawing on walls, but it's more about stellar flares. And so we see a lot of stellar flares on the sun, solar flares. So here's just an observation. Ooh, sorry, I didn't realize there was volume on that. So yeah, here is a huge and beautiful flare that happened on the sun. And I'll play it again just to see it. And while we can really resolve these events on the sun, we can't really do that for other stars. But what we can do is we can use observatories like the Hubble Space Telescope to observe these events spectroscopically to try and understand where flares form and then how they will interact with these close-in exoplanets. So that's exactly what we did. We have 2 visits with the Hubble Space Telescope to AU-MIC, which is our closest, youngest M-star neighbor. So 22 million years old, located around 9.72 parsecs away.
And this system is really awesome because it really is the system that just keeps on giving. So it's really close so we can get really high resolution spectra. It also has 2 very close in transiting exoplanets, and it also has a debris disk. So like any kind of young stellar science that you want to do, you can really do with this system very well. And this is a program that was led by a collaborator, Wilson Colley. I want to highlight that. So here's just one of the examples of the spectra that we got for AUMIC. It's incredibly rich. We were able to measure 170 plus emission lines from the star alone, as well as be able to detect its continuum. So just the general underlying flux where there are no emission lines, which is something that is really, really challenging to do for these M stars because they tend to be really faint. So this is one of the best cases where we can start to understand the effects of the continuum for M stars on exoplanet atmospheres. Now, what's cool about the cosmic origin spectrograph on the Hubble Space Telescope is it also has a time tag feature. So we can go in for our observations and create light curves and see exactly what the star is doing over the 5 hours of observations that we had. So what I'm showing here on the x-axis is time, and then on the y-axis is just the flux from the star. And for those who are unfamiliar with what flares look like in time series photometry, this is what they look like. I'm highlighting them in yellow. And so you have this huge flare in the middle of our first visit. That's known as flare B, B for second flare, but also B for biggest flare, conveniently. But then over the entire visit, we were able to recover 13 flares, which gives AUMIC a flare rate of around 2.5 flares per hour, which is just like insane, right? We don't see that for the sun. We don't even see that during solar maximum. So it was really cool to be able to see this for a 22 million-year-old M star, and then start to understand how this incredibly high flare rate will then go and affect the atmospheric mass loss for these planets. So the way that we did that was we did kind of a back of an envelope photo evaporation calculation for AUMIC B, which is the innermost planet of the system. And so what I'm showing here in the gray line is just an example of what that photo evaporation would look like if you didn't account for flares. So what you're seeing at the beginning of the time is the star is in the prolonged period of that high energy luminosity and then slowly declining over time. The points that I'm showing here when we start to inject flares into those calculations. And so you see that in the presence of these really luminous flares, 10 to the 32 ergs per second, 10 to the 34 ergs per second, you're getting instantaneous mass loss rates of 6 orders of magnitude higher than what you would expect if you were not accounting for these flares, which is crazy. And then if we estimate like how long AUMIC would be in its flare state for, just given the flare rates that we have, if you assume that every flare is about 5 minutes long in duration and it's flaring twice per hour, that means 1/6 of its entire lifetime is in this flare state. So that would tell us that these instantaneous mass loss rates of like 10 to the 12, 10 to the 14 is really dominating the atmospheric removal for these young close-in transiting exoplanets. Now, I just want to highlight that this really is like back of the envelope stuff, and there's still a lot of open questions that we have and better ways to model this, but this is really just kind of a starting point to get us thinking about how flares affect atmospheric removal. The other thing that I want to highlight is that these observations are not just about the planets, but they're also about the star themselves. So we saw a lot of really interesting things in the spectra. So what I'm showing here is just the continuum. So those regions where there are no emission lines when AUMIC is in quiescence, so it's not flaring. And then they're just binned by wavelengths. But when you look at these exact same points, when AUMIC is flaring, you see this really large increase in flux at these really blue wavelengths. We're talking 2 to 3 orders of magnitude in these shorter wavelengths. And this is really interesting. We weren't expecting to see such huge bumps in the flux like this. Previous observations of AUMIC had seen increases towards this range, but not to the extreme that we're seeing here. And so not only are we learning about the flares in general, but we're also learning more about the flare mechanisms and things that occur, physical processes that occur on the star during the flare events. And so there are lots of still open questions about what the heck is going on here, which is really exciting. And so with that, I just want to give you my takeaway points where we identified 13 flares over 2 Hubble visits, yielding a flare rate of around 2.5 flares per hour for our closest, youngest neighbor, AUMIC. We find instantaneous mass loss rates in the presence of these super flares could be one of the primary drivers for atmospheric removal. We still have a lot of unanswered questions about what's going on during these flare processes, like I showed you in those continuum points. And the paper is currently on the archive, and feel free to email me if you have any questions. Thank you.
little spinny beach ball of death here. Waiting for that to close. See if we can bring it up. Yeah, I think so.
Yes, can you hear me good? Yeah, thank you for sticking around till the end. My name is Rafael Luque. I'm a Margarita Salas Fellow at the University of Chicago. And I would like to thank the organizers first for giving me the opportunity to highlight this recent exoplanet discovery in our solar neighborhood, just at 32 light years away. And this is a work where all these people have participated in. There are more than 40 institutions represented here, mostly from Spain, Germany, and the United States. But particularly, I'd like to highlight the work from Dr. Fulton from Caltech, representing the highest instruments, and Dr. Kunimoto, who is also here in the audience, from MIT, representing the test mission. So now that we are in La La Land, let's get to know one of its stars, right? HD 260655 is the star of today's show, and obviously lives in Hollywood, right? With the rest of celebrities in the solar neighborhood. And for comparison, if the sun is located here in Pasadena, and HD 260655 lives in Hollywood, then the center of our galaxy will be located somewhere around Nepal, okay? So we are really talking about the solar neighborhood and a really nearby system when it comes to astronomical distances. So let's introduce the new celebrities that have arrived to the solar neighborhood. We have the host star, HD 260655, as I just said, which is a low mass star. It's also known as an M-dwarf, like AUMIC, Adina presented, who we know pretty well because due to its high brightness despite the small size. And the two new celebrities that have arrived to the neighborhood are the terrestrial planets HD 260655b and C. And a very interesting fact about these new planet celebrities is that they've been stalked for years by the telescopes in Mauna Kea and Calar Alto observatories, and they have been under the radar for a really long time, something that will not be any longer true, right? And the sloppy paparazzis were the HIRES and CARMENES instruments. These are radial velocity instruments, high precision spectrographs that can infer the presence of a planet by the so-called radial velocity method. This technique allows astronomers to measure the wobble that a star makes towards the line of sight of an observer due to the presence of a massive companion orbiting around it. This back and forth movement of the star creates a Doppler effect that moves the spectral line of the star spectrum, as you see in the diagram, to the red and to the blue. If we have a spectra with enough resolution to measure many of these lines, we can derive with great precision the orbital period and the mass of the object that is pulling the star back and forth from us. However, despite these celebrities have been stalked over 2 decades, CARMENES and HIRES data remain unnoticed. Until, like sometimes celebrities do, they were caught in the act of transit. And a transit is nothing different than the eclipses that we are going to see from the United States in the next 2 years. And for exoplanets, a transiting planet is just detected by measuring the brightness of a star over a continuous period of time and finding periodic dimmings that are provoked by the planet covering partially the face of the star. The TESS mission is one of the best in the business at catching these celebrities transiting in front of the star. You should not even consider a paparazzi. It should be something like a big brother that is monitoring for months or even longer, hundreds of thousands of stars trying to catch red-handed planets in the act of transiting. So TESS makes all its observations almost immediately public, streaming worldwide the lives and light curves of all the stars filmed in camera. And here we can see the 4th cameras of TESS telescope observing a region of the sky which is known as the ecliptic, and where the Kepler telescope, under the name of the K2 mission, spent the last of its days. So HD 260655 is located in this green square, and it was observed approximately from September to December last year. And as you may see, the plot here shows the brightness of the star as a function of time. And we can see some periodic dimmings that are caused by these planet candidates. If we look into more detail what this dimming It is occurring periodically and corresponds to 2 different planets, slightly larger than Earth and with great clarity, great precision. However, before publishing in the Yellow Press these results, we went fact-checking that these signals were true planet celebrities and not just some glory hounds. Right? So digging up dirt for this star, we went back to the archives and remodeled the Hires and Carmenes observations taken in 1998 in the case of Hires and 2016 in the case of Carmenes. And voila, the signals found in the test light curve were also present in the radial velocity data. Just were not significant enough to be caught before, but we could confirm that the planets are there, and this effect that we saw in the test light curve was not any other astrophysical source. So with all the data in hand, we tried to sell our story to the highest bidder. And then with a good clickbait title, we got our exclusive interview, Celebrity Masses and Revealed, right? It's pretty juicy to know the mass and size of a celebrity. So with the test observations, we were able to measure the radius of the planets, and with the Carmenes and Hires radial velocities, we were able to measure their masses. We found that these planets, despite being slightly larger than the Earth, they have a density which is pretty similar to our own. So this graphic shows their position in a mass radius diagram. And we can see how they compare with other known small planets. The colored lines here show different composition models. In red, for example, it is what a planet fully made of iron would look like. In yellow, a planet made fully of rocks. And in blue, a planet that would have half its mass in water. And we can see both planets are consistent with having a composition consistent with rocks. They touch this yellow line over there. And this allows us to call these super Earths, because before we only know the radii, and they were larger than Earth, we can call them rocky walls, because now we know their densities. Without their masses measured, we would have never known their composition. So this is an artistic representation of how the planets could look like. The sizes are not to scale. And here there is another representation. You know, in every interview, you need to put some pictures there. And then, of course, for the highest bidder, we sell them the ones dancing, right? So these are. So why are these planets celebrities? We know hundreds of rocky planets so far, and we are going to discover even more in the future. Why should we care about these ones? Well, these are VITs, right? Like celebrities do. And VIT means that they are very important targets for the recently launched James Webb Space Telescope. In this diagram, I just marked what it is considered to be a top quartile target planet for studies in the James Webb, or those dashed lines there. So the circle in the diagram represents planets similar to the Earth, and the triangle is these super Earths. And planet B is a circle here in this diagram, and planet C is a triangle. And they are both above the line that are marking the sides, right? So they are both ranking above the thresholds of what it is a top target for James Webb. And this is because the planets orbit a smaller star that is so close to us that is quite bright. This is actually the 4th closest multiplanetary system to the sun. And this fact actually greatly helps its observational properties with the James Webb. So to wrap a little bit, here there are some highlights of this new multiplanetary system. As I just said, it's the 4th closest, but if you consider only Endwars that are quiet, not like AUMIC, which is slightly closer, but a lot of tantrums, and single planetary system is the closest, okay? And this really helps for follow-up observations. And both planets are ranked among the top 10 best targets to look for atmosphere with the James Webb. And finally, it is a good example of what is the power of archival observations and observatory archives and their legacy value, right? Tests reveal these candidates from transit observations, and if we could confirm them so quickly, we are talking the observations we're taking from September to December. If we confirm them so quickly, it was thanks to the rich treasure of observation of nearby stars that Hires and Carmenes and many other instruments in the ground have carried out during the last years. And this one is not the first of such synergies between the test spacecraft and other instruments on the ground, and will certainly not be the last. So thank you very much for your attention. Happy to take questions.
Okay, we've got everybody in gallery view now, so I'll turn this back to Haley.
All righty. Well, thanks to all the speakers for their excellent talks. So we're going to launch into the Q&A. So we have some questions online, and people in the audience, please, and everybody asking questions, please remember to state your affiliation and who your questions are for. And for the people in the room, quick reminder to keep your masks on, please, when you ask questions. The microphones are really good at picking up voices. So go for it, Riley.
Hi, I'm Govert Schilling, freelancer from the Netherlands. I have a question for Michael and one for Ivan. For Michael, I was wondering, do you have any information on the velocities of your blue blobs, and does that tell you something about their origin? And a question for Ivan, you showed these simulations that would produce the rings in these disks. Is it still the case that people assume that these rings are due to the existence of planets, or can they arise in a different way? And in the first case, doesn't that just mean that these massive stars that you're studying, that they don't form planets?
So I guess I'll go first. Yeah, so all of those 5 blue blobs. Sorry? Oh,
Sorry.
all of those.
Okay, go for it.
Okay, sorry. Yeah, so all of those 5 blue blobs were observed with the VLT instrument called MUSE, and they're all detected in the H-alpha line, the H-alpha emission line, and that gives us a velocity. And so we kind of learned 2 things from that. The first is that all of those different clumps that you saw in those images, they're all at essentially the same velocity. So they're all definitely kinematically associated. And the second thing is we learned the velocity, the radial velocity relative to us. Some of them are actually moving towards us very slightly. They have very slightly negative velocities, and the highest velocity ones are about 1,000 kilometers a second moving away from us. And this is very consistent with them being in the Virgo cluster. And when you have a galaxy cluster, there's lots of orbiting galaxies around the cluster. And so you can see a wide variety of velocities. And basically anything in that direction that's has a velocity between about minus 500 kilometers a second, so they're coming towards us, or moving away from us at a few thousand kilometers a second, that's all totally consistent with Virgo cluster membership.
Great. And to answer your question for me, so I think the first part was forming planets in the rings. There is observational evidence that planets do form in rings. The discovery of PDS 70b and c are definitive proof that at least some of these gaps we do see forming planets occurring, though that number is relatively low. Extending that to the more massive stars, it's not necessarily true that they won't form planets. They almost certainly do form some planets. It's unclear how many. These more massive stars are going to be spectral types A and B type stars, which are notoriously difficult for planet hunters to find due to their usually distance and spectral features. So a lot of great new observations with TESS, and the new release of Gaia might actually illuminate how common these planets are around on these stars.
Hello.
Hi, everyone. I'm Ethan Siegel of Start to the Bang. I have a few questions, but let me start with one for someone who hasn't answered a question yet. So this question is for Tony Wong. When we follow the map constructed from ALMA data, it looks very much like it traces the filamentary structures of the densest gas clouds that absorb invisible and NIR light, with the ALMA data also extending a little bit beyond that in some regions. What is the ALMA data revealing about these regions? Is it showing us warm gas that's well on its way to forming new stars in the very near future?
Yes, hold on. Is this mic okay? Yeah, okay. So The ALMA observations reveal the densest gas because only the densest gas can produce the type of spectral line, the carbon monoxide line that we observe with ALMA. What we see with the optical image from Hubble is black features that also look filamentary. Those are basically produced by dust, which absorbs background light. So if there's any patch of dust between us and some nebulosity, then we can see the black filament in front of the nebulosity because it's absorbing that light. So I think what you're seeing in that three-panel view is a pretty good agreement between where there's that dust and where this densest gas is. But it's not total because the dust only absorbs if it's in the right place relative to the nebulosity. Whereas with the ALMA data, we basically see through the entire cloud. So we get basically a complete view of the gas, whereas if we were just relying on the optical data, we would have to make assumptions about where the dust is relative to the nebulosity in order to see those dark features. Okay, so I hope I addressed your question. Okay.
The test of if I understood what you said is if I can explain it back to you and you say yes.
Okay.
So are you saying that when you see the dust is in front of the luminous part of the matter, but when we see the gas, which ALMA sees, that could be anywhere in front, in the middle of, or behind?
Exactly. And that's why the ALMA data are so valuable. It sees everything.
Okay. All right, Ethan Siegel from Start to the Bang again. This question is for Adina. Adina, thank you for this presentation. I know you mostly focused on the star AU Mike, and I'm a little bit curious about the original motivation you talked about for this research about these young, puffy, super Neptune, sub-Jupiter worlds. Are we thinking that these worlds will settle down to become more like the standard Neptune-sized worlds that we find in large numbers via the transit method as stellar flares blow these, I don't know what to call them, planetary outer exospheres away? Are we able to get a spectrum for these puffy worlds and find if the outermost components of the atmosphere are all hydrogen and helium like you might naively expect, or is there something else going on?
Yeah, that's a great, can you hear me okay? Yeah, that's a great question and something that we're actively working towards. So yes, we do think that these planets will eventually settle down into that dense region of super Earths and sub-Neptunes. But the question of getting spectra for these atmospheres is incredibly challenging because the surfaces of young stars are just covered in dark star spots and bright faculae, which really contaminates any kind of planetary signal that we could potentially see. And so finding these young transiting planets is incredibly difficult because of that. Now, if you want to go after these with spectra, it's just like 100 times more challenging. And so we're like actively working towards trying to find and refine techniques to do this and to detect signatures of atmospheric mass loss directly. Unfortunately, for planets like AU-MIC-B, AU-MIC-C, and some of the like other young systems like B1298 tau, we've yet to directly detect any kind of atmospheric mass loss with a helium line. So this is looking for those like outer extended exospheres. And that's mostly because the stars themselves are just so active and it's hard to disentangle those signals. So ideally, yes, we would love to do that. And we're trying to do that, but I think it's going to take a little bit of time just because we really need to study these stars spectroscopically in really high resolution detail to be able to then say confirmatively that what we're seeing is from a planet rather than from the stellar surface itself. Does that answer your question? Okay.
Thank you. This is Romy from SAO. I have a question actually for Michael again. You mentioned that these blue blobs are formed from material that was released from a ram pressure. I was wondering if, because you mentioned that these are also very hostile environments that these are in. So does this say something? Can you talk a bit more about what the rate of at which the gas is essentially dissolved, for lack of a better word, in these hostile environments, and if the fact that the stars formed in these regions quickly enough before the gas was essentially dispersed can be used as a tool of some kind to understand the surrounding plasma in the region.
Yeah, so that's a really good question. I can answer part of it, but you know, these objects, we sort of recently discovered them, and although I showed that simulation, you know, that simulation doesn't really encapsulate everything about these objects. It doesn't produce things that are exactly the same as the objects we see. For example, the gas clouds in the simulations are generally too low mass to be the objects we found, and probably their metallicities would not match as well. So there's definitely, although that mechanism seems like a viable means to form these objects, there's definitely details that still need to be worked out. So I just want to start with that as sort of a caveat. But in terms of the objects and how long their gas can survive, there's actually 2 of those objects that still have cool gas. So 2 of the 5, and the other 3 we didn't detect any atomic gas. And so 2 of them are at least young enough that they still have that gas. It's very difficult to estimate exactly how old they are. But maybe the youngest ones are on the order of 50 million years old. And the oldest ones maybe 150, but it's really difficult to know that for sure. And I'm just talking there about the oldest stars. All of these objects have very, very young stars that are, you know, currently being formed. So that's just the oldest stars. But we don't really know when those stars started forming. So we have the gas being stripped by ram pressure, but we don't know how long that gas transited through the intercluster medium before it started forming stars. So we don't necessarily know how long ago that gas was stripped. And in terms of how long it can survive, I think that's really an area of active research. It might be as long as 1 billion years for a very massive cloud, but it might be much shorter. It might only be a few 100 million years. And that's really uncertain at the moment. And it's still, you know, people are researching that with simulations.
Okay, we have time for one more question. Carrie, is there anything online? Awesome.
I have a question for Rafael from freelancer Rick Lovett. What type of things might JWST be able to detect in these planets' atmospheres, given their distance and the type of star that they orbit? And how much better are they as targets than other Earth-like and possibly habitable planets?
Well, this is the key question, right? We were first in the stage of finding these candidates, and now James Webb is going to start answering questions for them. One of the long-standing questions in the field of exoplanet atmosphere is if those rocky worlds, which we have never had the precision before to observe their atmospheres, do have atmospheres at all, right? It could be possible that they have atmospheres or that they do not have atmospheres. And that's already a basic first question that we need to address, and it hasn't been impossible before. Once we have, if we simulate that these planets do have an atmosphere, these candidates are bright enough or orbit a star bright enough that in a relatively low number of observations, we would be able to detect features like water or methane or hydrogen in them. But this is only after we know if they have an atmosphere or not. How these planets compare to others? Well, these planets are a new discovery. It's a very recent discovery, so they are not part of the observations scheduled for James Webb during this year, but they rank among many other targets that has been included into the observations of James Webb for this cycle 1, right? So we expect them to be as good in terms of signal to noise as other famous candidates like GJ357b or the TRAPPIST, some of the planets of the TRAPPIST-1 system. So they rank among them.
Great, thank you.
Great. We are out of time. Thank you, audience, for staying a couple more minutes. So I just wanted to thank the speakers again. And thank you so much to the audience, again, for sticking with us. And thank you to the public information officers who helped with the press releases and the press briefing. Thank you to USRA and our other sponsors. Our next press conference will be today at 2:15 p.m. Pacific time in this room, titled Extragalactic Investigations and Evolved Stars. So we hope to see you all there.